Hi, my name is Catherine Zalagowski, and this is the Panamax class ship design outline process for Group 23. So the design requirements for the preliminary design. So we were tasked with designing a Panamax bulk carrier, and the vessel was to be built with steel as the primary material, and we were tasked with finding the optimum secondary material, and we talk about the secondary materials that we considered in a later slide. We were using a cargo capacity requirement of 70,000 DWT of wheat grain, which, and the ship also has to contain 5 cargo holds. The maximum dimensions for beam, length, and draft given were 32.2 meters, 294 meters, and 12 meters. So we had to make some preliminary assumptions and in our initial design. So the initial design was a box barge, as you can see in the CAD drawing below. And using the cargo hold dimensions and the wheat capacity, the wheat cargo was calculated to have a volume of 79,362.1 meters cubed. And the engine is a Wärtsilä engine with a weight of 2,300 tons, and we did some research, and this is a reputable engine with a thermal efficiency range above 50%. So it's a really efficient engine when it comes to working with the propellers. And we considered moving the engine to the midsection, but we decided that this would increase the stress of the ship, which we did not want.
For our initial design, we had to consider the different loading conditions of the ship. So the two main loading conditions we considered was an unevenly distributed load, where we had more cargo located at the back and front of the ship, and a evenly distributed one where the cargo was evenly distributed throughout all the cargo holds. So as you can see from the graphs, the unevenly distributed cargo load had a lower stress on the ship compared to the evenly distributed cargo load. So we would recommend using the uneven distribution if possible. So for our initial design concepts, we also looked at the stress versus the length of the ship and other geometrical parameters of the ship. So as you can see from the graphs, the smaller the ship, the less stress there was. So for our design, we ended up going with a 150 meter ship, since that gave us enough room for all the cargo, along with a little bit extra to play with if we needed more room for anything such as the engine, and also kept the stress to a minimum.
So after designing our initial ship, we had some design realizations and progress, and we wanted to make some changes to the ship. So we decided to taper the beam of the ship in the next design, and the ship had greater stress when the load was unevenly distributed. So when we increased the length of the structural beam, it kind of increased the stress and the deflection that was on the ship. We did several different parametric variations of ship length to see kind of what the stress would be and how it would change, make changes to the ship. And we found that 150 meters was an optimal length for the ship. And since this fit into the Panama Canal design constraints, it worked well. So the ship had the least stress when the load was uniformly distributed, as Nick talked about in the previous slide. So the final design of the ship would include 5 cargo holds, 1 additional hold for the engine, and again, we were going to keep the engine at the back of the ship. And so the next part of the design was to kind of find the optimal materials for the structural beam. So we considered 4 different materials for beam construction, and as you can see in our chart, we used aluminum, magnesium, A36 steel, and Kevlar epoxy, and we used these to make 3 alloys, and then we kept the Kevlar epoxy just as a material. And so we used 87% aluminum and 13% magnesium epoxy. We also did a 93.5% aluminum and 6.5% magnesium and epoxy, composite. And an 80% steel, 20% aluminum composite, and then the Kevlar epoxy. And so we used the law of mixtures to find the properties for the composites and for the material Kevlar epoxy. So aluminum is really light. It provides a large amount of strength. The steel is heavier than aluminum and it has a high yield stress. The aluminum magnesium epoxy alloys are very high in strength and they're very corrosion resistant. And then the Kevlar epoxy is used as a composite in ships and airplanes and other engineering structures.
So for the materials, we did a comparison of different ones versus the stress, and we used density as a proxy for the material properties. So as you can see from the graph, the Kevlar epoxy, which is the purple dot, has the lowest normal stress due to its low density and therefore low weight on the ship, and is what we chose to go with for our final design.
So weight reductions and stringers. So we confirmed that the maximum stress stayed below 60% of the Young modulus limit that was given. The maximum allowed deflection of 0.66 meters was also obeyed in our design. So we used the stringers to reduce the weight of the girder and the cost. And using the buckling formula, we found that the max length that the stringers could be was 47 meters, and this was kind of the max length that they could be to prevent buckling of the ship, which we did not want. We also used ribs to break up the spars, and they were long enough to span each of the sections. And these sections were previously selected for breaking up the cargo compartments. So final design, the final design had a height of 69 meters, length of 150 meters, a beam of 32.2 meters, and a water line of 10.6 meters. So we progressed from the box barge to a properly shaped vessel, as you can see in the progression of our CADs to the right. And the beam was constructed of Kevlar epoxy, which weighs 60,822.2 pounds. The corresponding cost was $220,705. This is lower than the steel alternative, which was $703,250. And after adding the stringers and removing the mast, the new deflection was negative 0.436 meters.
So for our final design, we ended up going with the Kevlar epoxy girder. We also ended up optimizing the weight of the girder by removing mast from different sections of the girder to reduce the cost and weight of the overall ship. So as you can see from our trend plots, reducing the dimensions represented in volume for the girder ended up in a higher shear stress. We ended up calculating that we could go up to 0.6 times the yield stress of the Kevlar epoxy. We calculated that number, and that is what our moment of inertia is for the girder we currently have. We also did calculations for the tip deflection of the ship, which are also in line with the ABS standards. And this is our final design.